Okay, hello everybody, welcome back. Today we are going to be talking about the quantum physics part of the CIE A-level course. I'm going to try and do this over 3 different videos, so do watch through all of them in order to get a full understanding. This lesson is going to be quite packed because there's quite a few pieces that we do need to go over. In particular, we'll be looking at electromagnetic radiation and its particulate nature. Then we'll look at the photon as a quantum of electromagnetic energy. We're going to use this equation, E is HF. We're going to recap electron volts, which we have come across before, you should have done. And then we're going to look at a photon having momentum, which we will briefly cover. Then we're going to look at the photoelectric effect, and we're going to explain the energy momentum of a photon using the photoelectric effect. So we'll go through each of these items in turn through an experiment. Now this one, it really works with the experiment, so we will run through this in the lesson as well. Okay, so let's start with a quick recap. If you remember, we used the electron volt as a unit of energy. So where does the electron volt come from? Well, typically it comes from the idea that if we have a set of plates like this, with, let's just say, 1 volt between them, and I make this end the positive and this end the negative, what's going to happen to an electron here? It's going to create an electric field of value E, which will be V over D, and then I can say that the force on that electron will be EQ, E times the charge on the electron. Now, if I'm dealing with an actual electron, I can say that the charge electron is E. So I can also say work is equal to force multiplied by distance. So if I put all of these together, that becomes V over D multiplied by E multiplied by D again. So the work done, the energy on an electron, these D's cancelled, and I get whatever the voltage is multiplied by the charge on the electron. So that's the work done. So that's going to be the effective kinetic energy that I give to an electron. Now, quite often, we do actually accelerate particles with voltages, and we want to know about how much energy we give them. So rather than doing it in joules, which often gives me a very small number, we use the electron volt. So the electron volt is a unit of energy equal to the charge on an electron multiplied by 1 volt for 1 electron volt. So it's just kind of a natural unit to use. So essentially, as a unit of energy, it's 1.6 times 10 to the negative 19 joules, because this equation here just collapses to it. When we're dealing with particle physics, we're dealing with usually very tiny, very weakly charged particles, but we often accelerate them by big voltages, so they have a lot of energy for something tiny. So it can get a bit confusing in your head. The joule is kind of designed around classical physics, things like an actual brick that you throw, that kind of has an appreciable energy in joules. Particles, the individual particle for a particle can have huge amounts of energy, but still in our classical world it's a very small amount of energy compared to throwing a brick. So how do we get around that? Well, we get around it using the electron volt. It's a natural unit, just makes the physics easier, and it's going to come up a lot in this unit. So short answer, whenever you see something given in electron volts, we can always convert it by saying 1 electron volt is 1.6 times 10 to the negative 19 joules. But you do need to know where it comes from. Okay, so now we're going to talk about the photoelectric effect and where we see it. This is something that it can work really well as a practical, but unfortunately it's actually really difficult to do in schools most of the time. And the reason it's so challenging to do in schools is to work properly, you need some pretty dangerous equipment. But I will try and show you in class how it would look if we had this dangerous light source, but actually I haven't found any suppliers that will sell to schools. We have whole catalogues of equipment, and we can't Just can't get it to be delivered to schools anymore. I used to have one at a school I worked at, but I suspect it probably wouldn't be allowed anymore. Let's explain why that is. So, photoelectric effect. It can essentially be summed up like this. What we have on the screen here is a lamp, and that lamp provides light energy. Now, what we have at one end here is a plate that we put metal on. And between them, we can try and measure, we have another plate over here. And what we do in reality is we put a voltage between these two plates. And so what that means is, if we have electrons in this region of space, well, we can now get a current going here. Obviously, at the moment, I've got just a gap, so nothing will happen. So what happens with the photoelectric effect is we find if we shine some light on a plate, we start getting electrons leaving this metal. And because these electrons are now leaving, we can actually measure a current going between them. There's lots of different ways, like I said, that we can do this in real life. A pretty common one is actually to get a gold leaf electroscope. Here we are. So this is one that can be done in some physics classrooms. So what we get is a charged gold leaf electroscope, like you've seen before, and because it's charged, the gold stands up from the plate. Then what we get is a large zinc plate, and we'll talk about why it has to be zinc. And what's important is we must negatively charge this, so it kind of has these extra electrons floating around on here. Now what we find is that plate will stay charged for as long as we like, but as soon as we turn on the UV lamp, what we see is the gold leaf electroscope seems to discharge itself. So with no light on it, stays charged. With the light on it, discharges, which is pretty weird. But essentially what's happening is what you see here. When the light is switched off, we don't get any electrons being emitted from the metal. When we do turn the light on, suddenly we do have these electrons. Now, the electroscope can only kind of demonstrate this relatively weakly, but essentially that's what we see. Now, there are some really weird things that we see here as well. One thing we see is that if we increase the intensity of the light, like I've just done, what we get is more current. So can you see we're getting more electrons appearing here? And if I turn the intensity right down, again you get fewer electrons. But the strange thing is, you don't seem to change the speed of these electrons. Right? If I increase it, we get some electrons going quickly, some electrons going slowly, but the intensity doesn't seem to have any effect on that. Now if I switch on here current versus light intensity, you can kind of see what that does, right? So as I adjust it on this simulation, as I drag this to the side, I get more current. But weirdly, these electrons don't seem to go any faster. However, if I get different light sources, and I make the light source more ultraviolet, these electrons do get faster. Still, if I turn down the intensity, I get fewer electrons. Increase the intensity, I get more electrons. So we kind of have two things that start to depend on each other. The maximum speed of these electrons, well, that seems to depend on the wavelength. As I turn the wavelength of this down and down and down, these electrons start to get slower and slower. No matter how intense I make it, the electrons, I don't seem to see any fast ones anymore at low light wavelengths or long light wavelengths. And yet if I increase the intensity, suddenly they go really... Sorry, if I increase the wavelength, suddenly they go really, really fast. And the intensity, well, that only seems to affect how many electrons I see. Now that's incompatible with what we understand about light. So let's just think about then what we've discovered so far. It doesn't occur if the radiation is below a threshold frequency. Let's look at that. Here I've got maximum intensity, and here I've got electrons flowing and flowing and flowing and flowing and flowing. And look here. So here, at about 552 nanometers, I'm not getting any electrons coming through. As soon as I go smaller than that, suddenly I'm getting some electrons. Now they're slow, but they're being given off. Second thing we see, the number of electrons emitted per second, well, that's proportional to the intensity of the light. As I reduce the intensity, I'm getting fewer and fewer electrons, but they're still appearing. Now it occurs the second the radiation is directed at the surface, so long as the frequency is above the threshold frequency. There's no delay. Let's try it again. If I turn this to 0, the electrons stop. The moment I turn on the light, I get some light, suddenly these electrons are appearing again. And we can see that the maximum kinetic energy of the electrons, in other words, the faster they get, that is proportional to the frequency of the radiation. And no matter how much I increase the intensity, look, these are still going slowly. Even though I've now got up to maximum intensity, it's not affecting at all the maximum speed of these electrons. They're only just getting through there. So what does this mean? Well, the theory of this as a light wave, it cannot explain that. If we think about how a wave works, a wave is a way of transferring energy without transferring matter. So if we're giving these electrons that are stuck on our gold leaf electroscope or stuck on something, if we're transferring energy to them to be able to escape, well, that shouldn't require, or that we shouldn't see these effects. And particularly, we shouldn't see it happening above a certain frequency. We should see that after a certain amount of time, each electron will have gathered enough energy and then it can get free. So, because that's the way that waves work. Instead, we're seeing these two things. One, we're seeing that there's a particular frequency below which it doesn't happen, a particular frequency above which it does happen. And the second thing is we start seeing electrons being emitted the second we turn on from it. Waves shouldn't do that. Waves should be giving electrons more and more and more energy until they can escape. So, what are the conclusions we can bring from this? So the first one, the fact there's a threshold frequency. Well, that tells us that the radiation doesn't build up. It can't be joined together somehow. Now, that makes perfect sense if light is a particle. If there are individual packets of light reaching there, sure, then that would kind of make sense why it doesn't build up, because one photon or one packet of light arrives, that gives it the energy, suddenly it can do it. Waves can't explain that. Number two, the number of electrons emitted per second is proportional to the intensity. Well, again, that supports the idea that the light is little packets of energy that's arriving, because then more intensity means more of those packets, and each of those packets can be given to an electron and allow it to escape. Number three, we see it without delay. It happens the second we turn on the light, provided it's above that threshold frequency. Well, again, that means that there must be a discrete or quantized, oh look, can you see how we're getting into quantum? There must be a quantized amount of energy, a packet of energy that is transferred instantaneously in one bit of light. One particle of light has enough energy to release an electron. Finally, the maximum kinetic energy of the electrons is proportional to the incident radiation frequency, but not its intensity. So what does that mean? Well, it means, and this is the important bit, it means there's a one-to-one interaction between one electron and one photon. It's saying that one electron on the surface of this metal, it can absorb or interact or do something, and we'll see later what it actually is doing, but it does something with a photon, and that gives it enough energy suddenly to escape. But it's a one-to-one interaction. If it has extra energy left over, well, it can convert that into kinetic energy, and we'll explain what that means next. So, we've spent the whole of Year 12 teaching you over and over again that light is, of course, a wave. Now, light obviously is a wave. We know light's a wave because that's how things like refraction work. It can only be explained by a wave. But the photoelectric effect tells us that it must also somehow be a particle. And we call that particle a photon. It's a particle representing a quantum, a certain amount of EM radiation. Now, it carries energy which is proportional to the radiation frequency. But interestingly, it has zero mass. So, we need to have some way of quantizing the energy of those photons. We need to say how much each photon has. And Einstein worked with Max Planck, and they were both two very smart Germans, who came up with this equation, that the energy of an individual photon measured in joules is equal to some constant, which we're going to name the Planck constant, multiplied by the frequency of that photon. Now, what we say then is that this photon, it is a packet or a particle of EM radiation. And this is how much energy it carries. The actual derivation of this, it can be done classically, and if you really want to be aiming for kind of degree level physics, go and look it up. It's just about doable with A-level maths if you've done FP 3 and 4. But it is quite challenging, so certainly not something that's necessary for A-level to really get where this comes from. Okay, so how can we express the energy of that single photon? Well, we've already said E is hf, but we also know from everything we've done with light that the frequency is equal to the speed of light divided by its wavelength. So that gives us an equation that the energy of a photon can also be expressed as hc over lambda. You've got two options, E is hf or E is hc over lambda. Now that means that the energy of a photon is inversely proportional to the wavelength of the photon. Now you kind of already knew that because you should remember again from year 12 when we think of the EM spectrum, we say that the shorter the wavelength or the higher the frequency, the greater the energy of those waves. So this is consistent with what we see when we're thinking about light as waves, but now we're talking about it in a particle sense. Alright, so what's actually really happening when we are releasing these electrons? What we say is we imagine that the electron is living in something called a potential well. In other words, it's stuck in a hole, and it's stuck on this metal. Now, if you think about kind of what we classically know about electrons, that kind of makes sense. We know that electrons are negative particles that are attracted to positive nuclei. So we know that in order to remove an electron, we have to overcome that attraction. So we kind of vision it as rather than an electric field, you kind of think of it as a gravitational field, because that's something that we're more familiar with. So we call this a well. Yeah, it's like a hole in the ground, but obviously in reality, rather than it being gravity that it has to overcome electrostatic repulsion. But we're going to say that, like being in a hole, if the electron gets enough energy, it can be removed from this hole, and then that will let it be free from the particle that it's attached to, or free from the metal it's attached to. So with that in mind, we're going to come up with this equation called the work function. And what we're going to say about that is we're going to give it the symbol phi here, phi, Greek letter, and we're going to say that is the minimum energy required by an electron to escape the surface of a metal. Now, if we tie together everything we've learned so far, we know that different light has different amounts of energy. If we go back to our earlier equation, we say E is equal to hc over lambda, or equal to hf. So that tells us that red light with a longer wavelength has lowest energy, green has more energy, and ultraviolet, let's say, has very, very high energy. So what does that mean? Well, if we're talking about this one-to-one interaction, remember we came back here and we said that the maximum kinetic energy implies that there's a one-to-one interaction. Well, we can say when the red light is absorbed by the electron, or it transfers its energy to the electron, well, that's not enough. So the electron can't escape its well. If we got, say, a medium intensity, well, that electron can just escape. But again, think about it in terms of a gravitational energy. The whole way it's rising up out of this well, it's converting, let's say, kinetic energy into, or it's having to do work anyway. It's having to do work against gravity. So any energy left over, it will only just escape, so it will have no kinetic energy left over. But for violet light or ultraviolet light, well, it gives it enough energy that that electron can escape the metal and have energy left over, so it can leave. And that is logically consistent with what we see in this simulation. If we go back to the simulation, if I increase the intensity here, as I go to a very long wavelength, no electrons at all. As I increase my frequency, decrease my wavelength, I reach a point where I suddenly start seeing electrons appear. And if I reduce it and reduce it and reduce it, I get to the point where these electrons are barely moving as they leave. Like we're having a one-to-one interaction here. Single photons of light are hitting single electrons and just transferring enough energy for them to escape. If I go, though, to UV, well, here I've got loads of energy being given. So only a small amount of the energy that each photon is giving is actually used to overcome the attraction to the metal. The majority of the energy can go into kinetic energy, and so they can get faster. And that's how we come back to this previous implication. We can say that the maximum kinetic energy is proportional to its radiation frequency. Well, that's because, if we think about it here, we can say... Oops, if we think about it here, we're saying that the higher the energy of the photon, the more energy is left over for that electron to convert into kinetic energy. Now, what does that mean? So let's try and come up with an equation for that. Well, what we can say is that this work function phi, that is the energy needed in order to escape, right? That's this green, or what I've just drawn with red line. So I have energy left over, and that energy left over is going to be kinetic energy in the particle. So the HF part, this comes from the photon itself. Yeah, we've said that the energy of a single photon is HF. If I'm giving that to an electron, well, any electrons that escape, that will have, well, that will take all of the energy of the photon. So all of that energy is converted into overcoming the work function, overcoming the attraction, and anything that's left over is mv squared. As an equation, then, we can say that the energy of the photon is phi plus a half mv squared. And that gives us another expression. We can say, well, what's the maximum kinetic energy of a particle? The maximum kinetic energy it can have will be hf minus phi. We just rearrange this and say, we'll make a half mv squared the subject. This is then the fastest an electron can be. If you think about our simulation, we do get a range of electrons in here. Some are fast and some are slow. You can see there's occasionally slower ones here. Now the reason for that, and we'll come on to this more in a later lesson, is that not all of these electrons are at the same depth kind of a well. Some of them are actually deeper. So when we look at this equation, this is the EK max. You get this from the electrons that are easiest to remove from the atom. Now, what we can also say then is that, well, there's a condition when emission is able to take place. So it becomes possible to take place if this is bigger than zero. Basically, if the kinetic energy of it is anything larger than zero, well, then that means electrons are being emitted. So that happens at the point where HF is equal to phi. So we get this concept of a threshold frequency. And the threshold frequency, if we rearrange to get F, well, we can say HF is equal to phi, therefore F is phi over H. So at this threshold frequency, any photons that are above the threshold frequency, they will permit emission of electrons to occur. So they'll allow the photoelectric effect to take place. Okay, that was quite a lot to go through. What I really suggest you do, make sure you're familiar with these observations and what they mean. Okay, we know from year 12 that light absolutely is a wave. But these observations tell us that light is absolutely a particle, because only particles would have this explanation. Once we accept that light is a particle, then we can use this equation to figure out the kinetic energy of particles or of electrons that are emitted, which then tells us the maximum energy they can have, and then from there we can figure out what is this threshold frequency.